The last lecture included a lot of material and ideas that are sort of on the fringes of the classical mechanics. Today we're going to do the stuff that every textbook has, with a little shift. The one thing that we're going to do involves what are called generalized curvilinear coordinates. We're going to introduce that right now instead of waiting for Unit 2 or really Unit 3. So you can get more details on that particular subject by looking ahead at those 2 units, which were included in the first part of this textbook. The whole use of that formalism, which is on the board here, all of this stuff right here. So this is the kind of mathematics that you use if you're going to work with relativity, in particular general relativity. So it's a good idea to go ahead and learn mechanics that way. And it's very powerful, and it's very cool. It's very, it simplifies a lot of things, given that you will be forced in physics to use coordinate systems, maybe developed based on waves, that are not orthogonal. These are called Generalized Curvilinear Coordinates, GCC. So we're going to introduce that today, but we're going to introduce it in connection with the simplest curved coordinate system, which is polar coordinates. 2D polar coordinates. That's enough material of a complexity to pretty well cover all the topics that that particular field of mathematics uses. So I'll go ahead here, because the first thing that I want to do is also derive the Lagrangian, and we might talk a little bit about Hamilton equations, but mainly Lagrange for today, the ordinary way. And there are 2 lemmas we need to learn, lemma 1 and lemma 2, that involve partial differential, chain rules. So, nothing too much new on this, except that we have connections to some outside stuff added. And that is, I'm not going to use that one right now, but this one showing lots of links that are interesting. For stuff that's coming later. Just to review, this is lecture 8. Just to remind you, we're working with this guy right here. Later on, next lecture, we'll take on that one. So today it's Irish physics. Okay, we've got lots of diversity in the field of physics, and we're right now centered around the city of Dublin.
Lagrange?
The main thing, starting right here, is to use the chain rules to develop the, well, let's just put it this way. We're figuring out a funny way to say F equal ma. That's what the Lagrange equations do. Newton 2 being written in fancy form. So, if you have a 2-variable function, that's 2 Cartesian variable functions, then a differential of that function, written the way we've got, if we have, whatever functions you're using, you have a f and a g, this can define a coordinate system. And just pick any continuous functions, it's probably going to give you something, a mesh of some kind. It's not going to be necessarily orthogonal, but we're going to pick one that is orthogonal, and that's the good old-fashioned polar coordinates. So that's our first deal here. Now I should point out, and that's put right here, that this is, we're going through the Unit 1 of and we're down around Chapter 8, 9, and 10 of 11, and 12 of the review unit. But this particular stuff that we're doing here, I decided to insert, so you won't find that in the actual text. It's looking at these lecture notes in order to get that. In any case, what we want, instead of just a differential of the general function, I want a differential for the radius of the polar coordinate system. And radius is the square root of x squared plus y squared. It's very simple, almost first day of calculus. And theta, the polar angle, also. I'd like to know about these derivatives here. Those derivatives make a matrix. It's called a Jacobian, and that's the key thing that you look for right away when you're working with these generalized coordinates. So I'm going to try to keep these screens coordinated, and in particular, if I go ahead and figure out each of the four, it's a two-dimensional system, so two-squared dimensional matrix, two squared equal 4 component Jacobian matrix, simply is cosine minus r sine, then sine theta, and r cosine theta. That's it. That's what you look for first. And all of this fancy stuff with the covariant and contravariant vectors is based on looking at this matrix. You got to get this matrix first, and then everything, including our Hamiltonians and Lagrangians that we're going to be building from it, come tumbling out if you know what you're doing. So that's the basic idea of this thing. Now there is some funny notation that you may not be familiar with unless you've been learning about these coordinates. And GCC, it stands for Generalized Curvilinear Coordinate System. And throughout history, I think beginning with Gauss, who's kind of the inventor of all of this, Riemann is a famous mathematician also involved in doing this. I don't know who it was that decided that the notation to be used for a generalized coordinate system was Q. Well, I guess it makes sense because these can be really queer coordinates. So therefore, Q that's the best I can tell you for where the letter Q comes from. But you will find it on almost all of the literature that's what we're using. We'll use it quite consistently when we aren't thinking about any coordinate system in particular. Okay, and here's the other thing that I think is really quite important to keep in mind in all of these equations that we'll be writing from now on, and that is we really don't want to keep having to write this thing. When you want to do a sum over some index, and you've got maybe 5 or 6 of them going here, then you've got sigma, 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 sigma. That takes a lot of wrist motion. We're trying to reduce, keep people from having, what do they call it, carpal syndrome. Well, here's a way to sort of avoid carpal syndrome, okay? Use what's called the dummy index sum rule. Dummy index m sum. The rule is simple. If an index is repeated on the same side of the equal sign, it's usually over where you're working, but it could be on the other side. And if it's just repeated on the same side, not on both sides. If it's on both sides, it doesn't make any sense to sum up all the equations and write them many times. You do the sum on that side of that. And in other words, you put in this thing. So we're just going to eliminate that right away. If you see 2 repeated m's in there, get busy and sum them when it comes time to evaluate. In the meantime, you're going to be doing algebraic manipulation with the thing, and then you don't have to pay any attention to that until it comes time to actually evaluate. Okay, so that's a key thing. Now, how do you make that job a little easier if you're doing a bunch of, we'll have some pretty significant homeworks that have a lot of sums in them. What I do, and maybe the m of the first term is here, but then you got a whole bunch of other terms, and the next m shows up being 20 or so terms down the line here. Draw a line between them, just to indicate, I'm going to sum over those guys, and locate them in your algebra. Okay, this is called visual location. All right. Now they don't do this in textbooks. Obviously, it's very hard to put a line in, you know, when you're doing type, right? There's nothing does that. Even math type doesn't do that. It's even hard to do it with well, you know, the language that we use. What's not Maxima?
Mathematica.
Math type, and then
Mathematica.
well, no, I'm thinking of the actual language that you use to write equations. I mean, I use it all the time. I can't think of the name of the damn thing. But anyway, even it has a hard time doing that particular. Pardon?
Like latex?
Yeah, latex. Yeah.
Excellent.
Yeah. There are so many varieties of it, that, you know, and people probably have ways to do that. But anyway, so this was the key thing. This first of all, our cues, but as I say, this indication here is okay with scratch paper, but when it comes time to write your dissertation, you won't have that ability to do that very easily. Okay, so let's get to work here and see there are two lemmas that we really need to do in order to do our fancy mechanics here in these GCC systems. Okay, this key lemma 1 right here is you know, quite crucial. And the idea is pretty simple once we've accepted what we talked about last time, and that was that whenever I do a time derivative, I mean a total time derivative, not parts. I want everything that's going on with this variable to be in the differential derivative that I'm talking about. I put a little dot over it. Okay, so that's our velocity, you see, of that particular dimension. It could be the VW or the SUV. That's back to our two-dimensional system on the freeway, or the pen and the ball when we were doing that. But it could be the pen x-coordinate and then the ball x-coordinate. That would make a four-dimensional system. It would be something over four things, you see. So these indices here, and that's the other thing about this, is that they really annoying. This guy Riemann or Gauss that did this. Most of the time, the variables that we work with, particularly the queer variables, they have their indices where an exponent would go. And if you're not used to that, that's really annoying. Okay, you have to get used to that. Can't do anything about that. If you do, nobody's going to be able to read your papers if you put this particular variables on the downside. Later on, we will. They're called covariant indices. These are the contras, contravariant. And we'll name all that very shortly here. In any case, we would normally just write Vm. Unfortunately, is an intensive variable, a contravariant variable, so we put its indices upstairs. More about that later. But in any case, what this is showing us here is that when I take the derivatives here, of this. In other words, when I work with not dx, but dx dt, the t's kind of cancel in this fraction here. So the Jacobian matrix that I have to deal with for differentials, of course, it also is the one that I deal with when I talk about the velocities that go with those coordinates. So that's our lemma 1. I mean, it's pretty obvious a lemma. But I decided to make a big fuss about it because there's another one that's not so obvious. It goes with it. And if you don't have these, you don't go to Lagrange land very easily. So, as I say, this Jacobian matrix, this is it right here, does double duty. It does a Jacobian for the coordinates themselves, but it also is a Jacobian matrix for the velocities. So we don't have to have a new matrix for the velocities that go with each of the coordinates in our polar system, or we're making a transformation to the polar system from the Cartesian form. Okay, so let's get that on the board here before we go on. Now, one of the things that I would probably say right away is another way to state this, is you don't need, I'm going to back off that for just a minute, you don't need another Jacobian for velocity. That's, you got one for the coordinates, it's the same as it is for the velocities. Now, very often, the actual functional definition of a particular queer coordinate system may be really queer. That is, you can't find an easy solution where you get the q's in terms of the x, y's, and the z's that go with the Cartesians. If that's the case, you would kind of be stopped right here, except for something that it turns out to be really neat. If it's the q's derivatives that you're talking about here, or the velocities that you're talking about, you simply invert the Jacobian matrix. That's really cool. This will work no matter what the functional dependencies, whether it's invertible easily analytically or not. If you have to solve a quartic equation in order to write the q's, don't do it. You just go ahead and take what you've got with using the Cartesian side and do the inverse of it. Or vice versa, if for some reason the q's are invertible, then you go back to Cartesian by the matrix inverse. Now most of the stuff that we'll do here right away are 2 by 2s. In fact, today that's all we're going for. Okay. So how do I invert r cosine minus r sine, sine r cosine? How do you invert in general a 2 by 2 matrix? It's so beautifully simple. Switch the diagonals, leave the off diagonals alone, but put a minus sign on it. That's it, except for the determinant. The determinant goes in the denominator. That's just a real quick way to get an inversion of a matrix that everyone should know. Okay, just bingo. You got the inverse, right? And of course, sometimes you write it down. It's always good to check it, right? Because this is the beginning of some calculation, and you make a mistake, not quite getting the inverse right, you're screwed. So these are you know, little hints that I give you to help avoiding getting screwed. And let me get this one up to speed here as well. Okay, if there's anything else I need to say, yeah, there's the thing written out in all its gory detail, just to remind you about the 2 by 2. Okay? All right. Now, see if there's anything else. Yes, I say always test your inverses. Make sure they give a unit matrix when they're put together. So this is quite an important equation right here. And this is an equation that I like to say it's equivalent to the completeness relation when you're doing bra-kets. You see, bras and kets in quantum mechanics, bra, ket, right? Okay. I'm going to make jokes all about these things. I won't go into that. But anyway, this is what you usually work with when you're just doing calculations with states. But there's this time reversed guy over here, this sort of contra-like, somehow contrarian-like thing called the bra that always has to be with her in order to make an actual number come out of some calculation. Well, the way I look at it is this contra that we're talking about is the index up, and the bra is the index down. So that analogy is worth it. This is called a dual space in mathematics. Okay. And the completeness relation, if you recall, is when you stick a ket bra in between them so that you just get rid of this. You get a sum over that that gives you a number that doesn't reference, in this case, the Cartesian coordinates at all. So this is just another statement that the Jacobian and the Cajobian are inverses of each other. And it's a jokey name, right? I don't think Jacob would like very much that we did this. He's pretty serious about himself. But anyway, this is what's happened. Cajobian is a nice name for whatever it is that you get when you take the inverse of Jacobian. Okay. All right. Let's see if there's anything else here that needs to be brought up. I think that pretty well. Any questions? Because now we got to make use of this stuff. And that involves getting lemma 2. And this is not quite as simple as lemma 1, okay? Because now we're going to be mentioning a double time derivative. Two dots. A total time derivative of x dot. Okay, and x dot is this sum. Okay, and you think, oh, that's no problem. It's just going to be the Jacobian and q dot dot. You'd be leaving this term out if you said that. Okay, because the Jacobian is still usually a function of your position. So when you take a derivative of this thing, you've got to take a derivative of this thing too. So derivative of product is two terms, and that should not be forgotten. Okay, and the polar coordinates very much dependent on where you are in terms of their various ratios to each other. Okay, so in general, this is a result that gives me acceleration of some Cartesian coordinate. In other words, at some point you're going to go around a curve, and you're going to be feeling forces due to going around the curve. It's that simple. And it's going to be this guy. Okay? So somehow we have to work that in to our mathematics in order to get an elegant derivation of the Lagrangian version of Newton 2. Okay, so go ahead and say, well, I know how to take a time derivative of anything. I just do a partial derivative with respect to the coordinates times the actual velocity of that particular coordinate. So at some point I've got to do a partial derivative of this with respect to each coordinate. So there's a sum here over n. Okay? This j matches that, this m matches that, and stays still. This is a dummy sum rule that I need to do. And then I can go ahead and put it into a very typical double partial differential that involves this little expression right there. Okay, let's get things up to speed on all of these guys here. And then an important point that comes up right away when we do all of this. And here's where we make use of that thing we made a little bit of a fuss about at the beginning of the last lecture. And that is that I can reverse the order of differentiation in partial derivative land. Okay, so this was on page 15 of lecture 9. So I got to do that. Now, one of the things that you might worry about is, do I have to also include the dependency of the velocity here? I mean, that is the time derivative of the queer coordinate. Is that going to mess me up? And the answer is no, it isn't. These are independent variables. That's the key thing here. Important thing about mechanics is that the coordinates and the derivatives of the coordinates, we call the coordinate velocities, are independent variables in mechanics. I'm able to specify as I throw something where I throw it from, that's the initial position, and how much velocity I gave it from that point. Okay? We do that in our simulations. You click the mouse, and then you drag a little velocity vector, and it takes off in that direction. Nice way to kind of show the independence of those. You have to make an independent choice for all. So given that, I am able to reduce this thing here just to a single partial derivative of x dot. This is x dot right here. Okay? So that leaves us with lemma 2. A time derivative of the Jacobian thing is not so bad after all. It's simply partial x dot with respect to qn. Well, that's an extra thing you have to calculate for mechanics. Okay, the simple Jacobian by itself, if you're just doing curve analysis or geometry, not needed, but we're definitely going to need that. Okay, let's get it on both sides here. The chain rule applied to x dot. Okay, well, we're about halfway there. Let's sort of sum up what it is we have here. Two lemmas, and it's off to the races using these two lemmas for F equal ma, Newton 2. Now I think what I will do is go ahead and bring this screen up to speed with the two lemmas sitting in the places they deserve, prominently at the bottom. And here I'll go ahead and figure out how we handle, well, kinetic energy. That's the quadratic form. It's going to have a GCC a manifestation, but mainly this guy, F equal m. Okay, how do you do that in curvilinear coordinates? That's really what we're after here. And this is what we have to do. Now, there are a lot of fine print things that are often left out in descriptions of derivations of this thing. It's pretty sloppy writing in a number of textbooks that I've seen. So I'm trying to avoid that here as much as possible. And one of the things that I'm going to demand is, remember when we talked about the mass matrix, when we were doing the superball stuff? And it was always diagonal. There was just the mass of the ball and the mass of the pen, right? Or the mass of the SUV or the VW, right? We didn't have anything but zeros off diagonal. Here I'm going to say, I'm getting ready here, and I'm willing to have off diagonal M matrices in the Cartesian coordinate system of this thing. Now this could be of many particles. So if I had, 3 particles, and then if I was letting them to run in 3 dimensions, I'd have 9-dimensional sums to do here. And I'm ready to accept that. Now, what in the world do off-diagonal M matrices have? Where's that show up in physics? It shows up when you're actually thinking about a particle running through a lattice. And you run into all kinds of funny side forces. And those are the off-diagonal components that you have to worry about. Effective mass components, effective mass tensor is what you're dealing with. Okay? So there's a place, that's what we do in this building, is worry about things like that. So I think it's good to point out that that's where this would happen. But in order for me to get what I want today, I must have the Cartesian version of the mass matrix be constant. I don't want it to be a function of where you are. Now, if it is a function of where you are, you've got to start over. But we're going to take that thing just to make things the way they are in most derivations of this Lagrangian system. So what we've got here is the F equal ma equation written in Cartesian land, okay? And we're going to try to bring that up to date with GCC, okay? And we're going to do it for polar coordinates in complete gory detail today. And that will, I hope, show you the power, why it is worthwhile to deal with Lagrangian and eventually Hamiltonian equations. So, we have a dummy sum rule right here. That would be over 9 things if there were 3 particles in 3 dimensions. We've only got 2 things, so there's 4 components of our matrix, and then 2 coordinate components. Now, this was the other thing. Remember, we talked early on about how force times distance, that worked out very nicely to be something that described it. If it was a change in coordinates and the force was constant, that was a change in the amount of energy. That would be a work, dW, d work, differential work, okay? But we're saying, if I'm going to dx here, I want to express the thing in terms of, and I use my Jacobian to write the differential, the first differential, in terms of the queer coordinates, the q's. Okay? So, and the other thing is that this f here, if it really is that, in other words, acceleration is that, dot, dot, we've got to put that in. So here's where we hang on our way to make a completely different kind of coordinate system work for us. Now, this is the trick. This is quite a trick when you think about it. And it's just the first of the tricks that Lagrange pulled in order to get himself into coordinate land. This sum is true term by term. Now, what I mean by that is, and I'll just state it right here, it still holds if all of the differentials, because these are independent, you see, I can set them all to 0 except for the one I'm interested in. So therefore, I can just drop having to do the entire sum. I can pick a particular m and just write it like that. That would be what we would call a generalized force right there. And it's a weird kind of Jacobian transformation of the Cartesian force vector. Remember, this is a vector that has 9 components. It's going to have 2 for us today. Okay? So these are also going to have 2 values. They're going to be r and theta. This is going to be x and y. X and y. Okay, x1 and x super 1 and x super 2 is x and y today. But these guys are going to be r and theta, the q's. Okay, so that's the equation that we want to work on. We want to get this thing in a form that is really beautiful. This is what we're really aiming at right here. Okay, so this is a trick, big trick number 1 for the Lagrange derivation, is to write the f equal ma in this funny kind of way. So it's just made of one sum over Cartesian variables for each of the q's, in our case r and theta. So far so good? Okay. This is what we're after. Okay. We have here the generalized GCC force component defined. Okay. And put that up everywhere here. Okay, that's the next thing we need to do right there. And so let's do it. Here's where we do the main trickery of the Lagrange force equations. Okay. And here, this is quite a trick. This is not something for the faint of heart. The physicists sometimes would have a hard time thinking of doing this. Now, what I would ask you to do at a certain point later on in this class, just stop and see if you can remember all the steps that we did today. See if you can derive Lagrange equations. That's a good exercise, just to get you used to the trickery. The trickery here is just to use the differential relation a dot dot b is equal to the first derivative of a dot b minus a dot b dot. That's just the derivative of a product, right? Turned into a funny equation, right? That's the trick. That's it. Except you got to know what to do it with. And also have some idea why you would do that, okay? So we're going to do it to A, which is a sum over the mass matrix involving the sum K, and then the B is just a Jacobian. And the Jacobian obeys some simple lemmas, which are at the bottom of the screen and at the end there, and that's going to give us Lagrange equations by about here. Okay? So it's really a couple more steps is all we need. All right? Okay. Now, here's where that whereas, the fine print, goes. I can't pull these tricks off unless the Cartesian MJK are constant. Okay, the mass can't be getting bigger or smaller. Okay? That's a big deal when mass gets bigger and smaller, right? MC squared, a lot of energy. Okay, so that's a pretty good thing, but what do you mean by mass? Do you mean effective mass? Do you mean group theoretical mass? Blah, blah, blah. There are all kinds of different kinds of mass. So this could be an annoying thing for other applications. But what we've got here lets me just forget about these constants here as far as these derivatives go. And I do this, it's not going to do anything with that. It's just going to be affecting this and this. And the same thing, well, this one has already been spoken for, so we don't need to do anything too much more there. But anyway, to make a long story short, here are the tricks that get played here. First of all, what this boils down to, right here, I've gone too far, punched it twice. What this boils down to right here is a total derivative here of the this xj cubed, time derivative of that, okay, this guy right here, let's see if I got that right, yeah, that's fine. I'm going to replace partial x cubed with partial x dot, q dot. And you say, I'm making the equation more complicated here, why do that step? Because what I'm really after here is getting an equation that involves derivatives of kinetic energy. We almost got it here. I pull this partial derivative off of this thing. I've got an x dot k, x dot j with the mk. That's kinetic energy, so that's to be treasured. And the same thing right here. This is the second lemma. Okay, the time derivative of Jacobian is just a Jacobian, but with velocity in for the coordinate on the top. No change here. Okay, we're almost done now. Okay, all I have to do is meld those together nicely. Okay, and here's just sort of writing that equation here. I'm writing it out with a little v in here for the x dot. So I'm noticing that the partial derivative with respect to the coordinate of v squared over 2, 1/2, that's the kinetic energy velocity factor, okay, is this. Okay, that's the neat thing. And where q may be either q dot or q, depending on whether you're looking at this one or this one. So you end up here with a derivative with respect to the velocity of m velocity squared over 2, and here's the coordinate derivative of m times velocity squared over 2. Kinetic energy in both cases, okay? And that's the Lagrange equation for force, acceleration effect, for Newton 2, okay? So this is a big moment. We should stop and pop champagne bottles and drink from them, maybe, depending on your religion, because this is a big deal to have an equation here that's just about ready to be an equation that's entirely written in terms of kinetic energy and queer coordinates. You now have an equation in queer coordinates. Well, coordinates and the velocities of the queer coordinates. Okay. And remember, these coordinates don't have to be orthogonal or anything. It can be wave fronts crossing each other. All right, let's see if there's anything else I need to do here. Just go ahead and rename them. That's it, right there. Now, this is an equation that isn't celebrated enough. We're about to go to the Lagrange equation that you're probably used to if you've taken a good mechanics course, that involves a Lagrangian. But I want to get the one that involves kinetic energy, because it isn't always the truth that I can make a Lagrangian. In order to make a Lagrangian, I have to have a conservative system. It has to be a function of a potential. Okay? The force has to be a function of potential. All right? That's the second stage. Let's look at what's on the wall up here. In particular, let's look at this. This is what we just derived. I call this the Lagrangian derivative equation. It involves a force component for each of the dimensions in your system. And what it does, and that's, I'm going to point this out very quickly here, is it defines a momentum for you at this point. Okay, so we're at this point right now. We have a lot, about twice as much as we've had so far, because we are taking account of something that's feeling a force. All of the other stuff that we've talked about so far, the SUV and the superballs and all those things, they had forces between them, but they didn't have a force on the outside. Nobody outside was changing the momentum. Now it is. Now it is changing. And we're accounting for it fully. And the vector notation for it is this. If you're going to use Gibbs notation. Velocity here, position here. It could be a multi-dimensional position. That doesn't change. Okay. Let's see if there's anything else I need to say. I think we can go for it. This is the next stage. Right here that we're going to be fiddling around with. And that is the conservative system. So things are really a lot simpler if you have a conservative force field. A force that can be expressed as a gradient of a potential. If you have that, then you get what most people call the Lagrange equations. But let me extol the virtues of its humble beginning, that is this thing. I call it the four-wheel drive garbage truck of mechanics. That is, it can go anywhere and take a load of crap. So when you're stuck on a physics problem, because maybe your potential isn't quite what you thought it was, and you want to go back and you actually know the forces, this is the one to go for. It works. It works whether you're an accelerated frame, you can even throw relativity into it, you name it. This thing can go anywhere. The ones that we're going to come up with, the potential Lagrange equations, the ones that have an L in it, that's very special. And so is the Hamiltonian usually, as we go next step in this development on the lectures that follow next week. Or, we'll look at the calendar in a minute here to tell exactly what's going on. But in any case, this thing right here is definitely to be extolled. But let's go for the one that works the most when you're doing studies of particles and fields and so forth. Well, electric fields. Magnetic field takes some extra work. And the reason the magnetic field takes extra work is that this U here must have no explicit velocity dependence. So this is some more footnotes, whereas fine print that has to go onto the thing that we call the usual Lagrange equation that involves the thing called the usual Lagrangian. Okay, the Lagrangian that's a function of position and velocity, but also has this thing attached to it. This is a funny kind of energy now. Okay, you used to, when you say total energy, you're used to saying T plus U. Kinetic energy plus potential energy. That function has another name. Okay, that function lives in Dublin. That's Hamilton's function, Hamiltonian. Okay, we're back in Paris. This is Lagrangian. Okay, big difference. That is a sign error you do not make. Okay, but in any case, once you do that, you see, once you are able to write the L as T minus U, then you go through and you take this equation and convert it to that. Okay? You put the force inside here as the derivative of Q with a minus sign. That's pretty cool. That's pretty weird. But look at what you get. You get something that really has wonderful symmetry. This is the way I like to write it. Now we've already seen this one. Okay, I'm sorry. We've already seen, let's see if I'm stating it correctly here. The derivative of the kinetic energy, yeah, that's right. This one, this is our first equation here, where the momentum is the velocity gradient of L, right? We got that by geometry. Okay? What we didn't have was this one. The rate of change of this thing, the momentum, p dot, is a derivative with respect to a coordinate. And in our case, with everything we studied so far, it didn't matter where you were, the kinetic energy was being conserved. Now it's not. But look at the symmetry here. If I take the dot of this one and just drag it off of the Q and put it on the P, that's this equation. That's the way to remember the Lagrange equations. Both of them. The dot either goes here or it goes there, and it's a P equal a derivative with respect to Q in either case. That's kind of neat. Okay. Well, let's see if there's anything else that I need to comment on. Yeah. If L has no explicit Q dependence, and that's what we've been talking about before, if it doesn't depend on where you are, P dot M, that particular component of momentum, doesn't change. That's a conservation law. That's Lagrange giving you a conservation law for the momentum. That particular momentum, okay, it may be that it's independent of QR, but not of Q phi, or vice versa, which we will talk about today. Okay. If it's not a function of Q phi, that means the phi polar angle, you've got a conservation of angular momentum. We're going to show that very quickly in a few minutes. Okay, let's see if there's anything else. All right, now we have to do this task right here. And that is, go ahead and introduce some of the inner workings of the coordinates that make it possible for us to do relativity, but it also makes it possible for us to write very quickly any Lagrangian equation that you can possibly do. Now, this coordinate here is more civilized, shall I say, than GCC. This is called an OCC, a coordinate system. That means orthogonal curvilinear coordinates. And you can see they all meet at right angles except right here. That's a singularity in the Jacobian right there, and the Jacobian. Okay? But everywhere else, to infinity, this is golden. It's just right there. The thing goes berserk. Okay? And when we study complex variables, which will be the last two lectures for this review unit, you'll see some analogies to all of this, the coordinates that you get just by defining a complex function. As you have a real zoo of curvilinear coordinates, but every single one of them is an OCC automatically. And we'll see what that is all about. That's called being analytic function. Okay, so here's our Jacobian, here's our Cajobian. We've already worked that out. The trick is to notice that the columns of this are what we call covariant vectors. These are vectors that slither along the line that they're assigned to. This is an E sub phi, so it's always tangent to the R line, the R equal constant line, in the positive phi direction. I'll make that point more clearly in just a minute. But that is basically what we're what we do. Now the contravariants, the others, they turn out to be gradients. That's these guys right here. They turn out to be gradients of a particular coordinate line equal constant. So those are that's what I need to show in clearer ways. And this is the clearest way I can think of right now, just doing a sketch. But I warn you, these sketches are 2D drawings. Everything in here has got to be in this plane. They kind of look like they curve up out of the plane. They don't. Everything that I'm drawing here, all the curvilinear coordinates are just like this set here. They all lie in the plane of the screen. But here I'm imagining things sort of curving away, and you get the feel that this is something that's... What we're talking about would be true for something that did that. But this is a coordinate system I sort of imagine where Q super 1 is 100 on this line and 101 on this line. So it's gone up by 1 unit. In other words, dq has gone up by 1. This is 1. And then this is 1 as well for going from here. This is 200 and that's q2 equal 201. So this is just some crazy coordinate system picked out of God knows where. And it has, as a vector, something that's really close to how long it is to 201. And this one right here starts out tangent to this and has a length that's very close to however far it is along a curved line to q1 equal 101. But basically all of this is based, all this hand waving about here is based on this relation, the first differential relationship. That is E sub 1 and E sub 2, E sub r and sub phi over here are each these vectors here. This particular vector here and this particular component, okay, of that. Those are the two components in x and y coordinate system of this particular vector. So it's always going along these, and it's approximately, you can see how good it is, approximately the length to the unit change in some scale. There's some scale that makes sense here that would involve radians times about 1.2. Anyway, the other set, the opposite set, this is kind of the bras, the kets, the ones that have their indices up like, well, like the Ion Contra army, they had their machetes up in the air, right, after the Sandinistas. I don't know if you guys, I'm telling my age by the fact that I lived through that scandal a long time ago. But these are the Contras, okay, they've got their indices up. These are the, what in quantum mechanics you would call the bras. These are the kets, okay. They're weird because you see what they are the gradients of the coordinates in question, and you can see that down here. Here is E super 1 right here. It doesn't point along that; it points perpendicular.